Okay, everybody, we should be back. So now's the time for a Q&A. So Ricardo, if you're still around, you had a question about the ocean, I think.
Yeah. So what I wanted to understand is for the fully coupled ocean model, if I start from, I don't know what would be a possible initial conditions that you would put in that OIC file. I don't know, an ocean that is not going anywhere at some temperature. I don't know what it is, but for some initial condition of the ocean, and with current atmosphere for Earth in terms of, whatever is the appropriate parts per million in terms of various gases. So with a given forcing, how many years does it take for that ocean to equilibrate with the atmosphere?
It's a good question. It depends.
I can take that.
Go ahead, Kostas.
So I can tell you my experience with Planet 2.0 that we are finalizing. And it depends on the ocean resolution that you're using. And but it can take at least 1,000 years. And I can also add that if you are using Planet 1.0, for reasons I do not fully understand, probably just different physics, it takes a little bit longer. So you really need 2,000 years for Planet 2.0. If you're starting from just the default, whatever initial conditions we are using.
Yeah. Okay, that's extremely useful again.
And but I have to say that depending on the case, and it might take longer or shorter. And if you are using an aquaplanet, for example, it might take longer. And obviously, as Mike said earlier, change the ocean by 1,000 meters deeper, and you might need another millennium just for that. You don't know. It's very sensitive to the depth that you're choosing.
So when you were saying 1,000 years, did that ocean had realistic basin depths?
Yes.
Okay, right. So that's, yeah, so 1,000 years is very good. I mean, it's reassuring that it is that long, because now that we have clear data actually for ocean circulation, what you find is that, I don't know how you would define an average, but it's a typical parcel of ocean will take 200 years at least to circulate and say have been in contact with the atmosphere, whereas there are parcels of water that take about 1,000 years to really circulate. So there is this, I'm not interested in this for that particular reason, but it is one of the reasons people are saying, okay, now we've reached a point where the oceans are not going to take it anymore, and the global warming now is going to start being noticed in the atmosphere, not the oceans.
Right. So I want to say two things. One is that the key point is to equilibrate the deeper ocean. And it's not about how long it takes to meet the atmosphere and go back. It's about the heat to diffuse or get transported by currents at the deepest, at the lowest depths of the ocean. And then equilibrate that. This is what takes most of the time. It's not currents going around, it's currents going down and heat penetrating to the depths of the ocean. And the other thing that I want to say is that for Planet 2.0, we plan to provide you with the RSF files, the equilibrated RSF files of every template we will be having.
Okay, great.
So if you're planning to start from to do exactly that or something similar to that, you might get away with 100 years.
Okay. Now, incidentally, when you reach equilibrium, it's some dynamical equilibrium, but how do you define that equilibrium?
I can say that from the radiation standpoint, which is our switch, our check that contains everything, the net radiation of the whole planet is neither increasing nor decreasing.
Okay.
So if your ocean starts to cold, then it needs to take up some heat, and then until it equilibrates. If it starts to warm, then it needs to lose some heat until it equilibrates. The moment the planet itself is near zero, then we say that this is in equilibrium. And whether there are things to check on the deep ocean to see whether that equilibrated or not, I will pass it to Tony. He might have something to say, but usually we check the net radiation of the planet.
Okay, thanks a lot.
Yeah, this is the same for the ocean. That's the criterion we use for to say when we reach equilibrium.
Okay.
Yeah. In the AIJ file, there is a parameter called net_rad_planet_hemis. If you look at the global value for that, averaged over, say, a 10-year climatology, if it's less than plus or minus 0.2 watts per meter squared, we consider that to be in balance, basically. Some GCMs are more liberal with that. From what we understand, they allow up to a whole watt, but we try to maintain a bit more strict. So when Kostas is saying near zero, he means we're literally plus minus 0.2. And so that's what we check typically to see if the model's in equilibrium or not.
Yeah, great.
You can also extract the heat content from the OIGL diagnostics and plot the time series, and you will see at some point that the ocean reaches its own equilibrium.
Okay.
Okay. Any other questions from anything we've discussed today?
I have one. I try to access the R files for the impact of planetary rotation rates, and I'm getting a 403 forbidden error.
Okay, which file are you trying to access?
The rundex for the impact of planetary rotation rate.
Okay, well, Steve, why don't you send me an email for the path, because I'm not sure exactly which one that is, and I can just check the file. It might just be a file permission error, so sorry about that.
Okay. Where I was going to look for that is for having an example of a run deck that would be half or 3/4 of a day. The only thing that I would need to worry about changing in the run deck is the rotation period, and then confirming that it's not Earth.
Right.
Okay, cool. Just want to make sure with that. And another thing that you've alluded to, making changes in the atmosphere of things that are already in equilibrium. How would you go about simulating, say, an asteroid impact where you had a great deal of particulate matter or water, hot water that was in the atmosphere?
Yeah, that's that's a very difficult thing. I would say we have not done that explicitly in our model, but Kostas can talk to the point of how we handle volcanic eruptions in the model, which is a similar process. So Kostas, maybe you could just mention briefly, because it's a very complicated scenario. But Kostas, he's one of the experts that handles volcanic emissions. They simulate Pinatubo eruptions and things of that nature. So Kostas, why don't you say a little bit about that, perhaps?
So there are two different ways to simulate volcanoes. The simple way is that you prescribe some forcing that happens in the stratosphere where you expect the aerosols to be, and then that calculates, and that forcing is transient, so it moves around from, let's say, the tropics to the poles until it goes away completely, and then you see how that affects climate. And where this forcing comes from, it can come from a different simulation. There are sources for that. The other way to do it is the expensive way. So you explicitly simulate the aerosol formation with tracers in the model. So in that case, you need to provide input of how much material has been injected and where, and then they let the model chemistry and physics do the trick for how this evolves. Assuming you don't want the second one, because this will be harder, and you want only the first one with the asteroid impact, you need to think of a number of pieces needed, and I am pretty certain I will be forgetting some key ones as well. So one is where in 3D this happens. Does it happen? How does the asteroid come into the planet? Does it make a small trajectory through the atmosphere and then passes through several boxes, leaving a trail behind? Does it just go all the way down head first and sweeps a column and then hits the ground? Does it break higher up, or does it break after the impact? And then you have to worry about where to deposit the heat that is coming with it, especially if there is an impact, and hope that the model will not crash by that amount. And also, if you're talking about water, where to put your extra water. So we have put water through the volcanic eruptions quite a lot into the stratosphere, and the model was happy. Whether we passed the point that we modified significantly the mean molecular weight of the atmosphere in those small places is a question, but this goes away pretty quickly, so it should not affect you dramatically, and because you're not going to put something like 20% of water in the atmosphere, right? It's just some extra amount. The aerosols are more tricky. As long as you do not have any forcing to introduce in the model as external source that will evolve and go away with time, similar as I described with the volcanoes, then you will have to go through with prognostic tracers. And it's not impossible. It is slow compared to the climate, but this is a transient event that will go away after, I don't know, depending on the size of the asteroid, I guess. But it will go away pretty quickly. And so it's something very possible, but you will probably be needing help from us, which we can provide.
Very cool how involved that is.
Yeah, that would be, just to mention, that'd be quite involved. I would think that would be a collaborative project. So you'd probably want to talk with Kostas and Igor about what you have in mind. Go ahead, Igor, you had more to add?
I just want to mention that actually we presented something, well, it's not asteroid impact, but something similar. It's a major volcanic eruption on the moon. That's what I was doing actually for the past like a year. And you can look at our presentation at the AGU or LPSC. So basically what we did, we just set a major eruption just in one GCM cell and basically modeled it well, kind of properly, so that we have flux of the water and heat at the bottom of the, at the surface, and just simulate how basically water goes into the atmosphere and how it precipitates. But it's done for very thin atmosphere. It was done for 0.1 millibar. I guess, was it? Yeah, I guess most of the no, for 1 millibar. So most of the simulations were done for 1 millibar atmosphere. So such atmosphere cannot hold much water. So basically, it quickly precipitated. Basically, in 3 years, everything went down to the poles pretty much. But yeah, you can do this, but you cannot force the model too much. I mean, volcanic eruption still okay because it happens over the period of like 100 days, I guess. That's what we were modeling. Like when the planet is hit by impactor, that happens in a matter of seconds, probably. So you cannot just put as much stuff in the atmosphere immediately. So you would have to use some kind of approximation and like do it slower over the time so that the model doesn't crash. But yeah, I guess you could do something like that. Yeah, so
Great.
that's what I wanted to say.
Thanks, Igor.
Yeah, and since I have opportunity to talk. I just wanted to mention about the planetary index in general. Mike mentioned that there is one place where you have to put the planet name. Actually, there are two places where you have to put it. And the first one at the top is more important. It's like if the defined statement where you define that your planet has certain name. And that's not just giving the name to your planet, but also such statement as define planet. It basically changes the logic of the model. So before this defined statement, everything was treated as Earth. When you have this defined statement, the whole model switches to non-Earth things, and a lot of mechanisms are enabled in the model so that the model doesn't assume that you are on Earth anymore. So that's kind of critical thing. Like if you are doing Earth or you are doing something completely different, this defined statement basically it's a key thing, like to switch between these two types of the model.
Thanks for bringing that up, Igor. We should add a line to the tutorial slides on that. Absolutely.
Yeah.
You need it in two places. That's very true. Okay. Any other questions about anything we talked about today?
Oh, sorry. Did somebody else just start to talk?
No, go ahead, Nicholas.
Oh, go for it.
Thank you. I was just wondering about the limitations of the model with respect to planet size. You mentioned that sub-Neptunes are like totally out. And the Kane paper on Kepler 1640 something is like 1.1 Earth radii. And I was just curious, like what's the breaking point? Is it like base pressure, or what starts to go wrong as you make the planet larger?
Yeah, that's a good question. I haven't actually done any of those kind of simulations in the last few years, so I don't have a solid answer on that. I think that we've gone up to something like 1.3 Earth radii, assuming the same density as Earth without any problems, but maybe Kostas has something more to say on it.
I don't have something more to say, but I think from meetings that we had, the main problem was not the planet's size, but the increased gravity.
Absolutely.
So,
yes.
So if you have a lighter planet, which is bigger, maybe you are lucky. But if you have a denser Earth, you might get a crash. That's my understanding. The G is the problem.
Absolutely. That I was getting.
Yeah, that was also my understanding. It probably can be fixed. I guess we just didn't play too much with bigger planets, but it looks like just your dynamics gets unstable because the pressure force is too high. So maybe just going to much smaller time step could fix things, but we didn't try it, so I cannot say.
Well,
sure.
at least in the experiments I did try smaller time steps. It still was quite unstable, but it's just a regime we haven't looked at too much. Probably if we put our efforts there, we could probably resolve some of the instability issues.
Gotcha. Okay, thank you so much.
No worries.
Mike, if you don't mind, I'd like to add also, there's the issue with the scale height as well, with this getting into the sub-Neptune atmospheres. And the primitive equations in the dynamical core essentially assume a shallow atmosphere, and just about every GCM that you see out there uses the primitive equations rather than the full Navier-Stokes. So that's the limitation that comes in for trying to do sub-Neptunes with hydrogen-rich atmospheres, where kind of regardless of what their gravity is, that the dynamical core starts to be, it's not going to crash on you necessarily, but it's not going to necessarily be reliable given the constant gravity approximation and the thin atmosphere approximation that goes into the primitive equations. Now, saying that, there are lots of other people who just go right ahead with primitive equation GCMs for hot Jupiters and sub-Neptunes, and your mileage may vary. That comes with a warning. A warning label is attached to those applications.
Okay, thank you. Thank you for clarifying that.
It's a good point that Eric brings up in a sense. It's very easy to abuse these models and push them into dynamical regimes or areas where the model is probably not giving accurate results. So that is one example where you're not in the thin atmosphere approximation, but the model just keeps on running and can just be giving you rubbish. And there are others that we have seen in the literature where people have abused the models in ways that were quite appalling, but it just comes with not knowing the models very well. I mean, they are, as you might imagine, very large black boxes if you're not one of the core developers. So I think a rule of thumb for using this model is if you haven't seen us simulate it, you might want to query us to ask us if what you want to do is within what we consider the valid regime of the model. You know, for example, people are very interested in doing inner edge of the habitable zone studies. But if you go too far in, you start loading the atmosphere with a lot of water vapor. That changes the mean molecular weight of the atmosphere, and your dynamics will start being wrong, for example. So to be very cautious about that. Or, for example, there are ways to push the model's radiative transfer scheme, if you're lucky, beyond 400K, but you'll get warnings. But if you don't notice the warnings, you just keep on running and you might think everything's okay, but the model is actually producing a lot of garbage. So you have to be a little careful when you're pushing beyond the bounds that I've discussed in some of the slides.
Yeah, that's really important. The fact that the model will not crash doesn't mean that the model is right.
Yes.
You always need to remember that.
Yes.
Would you say that there's generally like, you said that it's like very well like documented and tested. Would you say that generally, like if you're going outside like the proper regime, there's going to be some warning that says like, hey, I'm not braking, but you better be careful.
It
or
depends.
is that
It depends.
okay?
Sometimes there will be warnings and it'll be clear. Other times, for example, mean molecular weight of the atmosphere, there will be no warning. The model probably will just run just fine.
Yeah, the model can't even detect that.
Yeah.
Okay.
Yeah. So the main, I would say that check the things that we have done in the past. Some of them are outlined at the beginning of our presentation today. And if you think that your case falls somewhere in between those, you're probably okay. But if you are extrapolating from our cases, maybe you are going too far and you need to check with us. It's only an email. I mean, it should be straightforward should be an easy email to answer, but you should contact us.
Okay, certainly. Yeah, we'll do. Thank you.
Yeah, about the warnings, yes, there are some warnings and there are some errors also. Like sometimes the model would stop if it thinks that you went very far from normal conditions. Usually in a lot of run decks, we have like maximum and minimal temperature for the ground or for the snow. That's because in Earth model, we assume that they should be basically close to Earth, should not like go out of normal Earth conditions. And for exoplanets, we of course extend those, but when you put such limits, you shouldn't like give yourself infinite basically infinite brackets. You should put still something reasonable that you expect, so that if you're expecting the model to heat up to like say 300 degrees Celsius and it goes to 1,000 degrees Celsius, then it should stop. So you shouldn't allow the model to do this. At other places, you just get warnings, and pretty much, I guess, you should know which are more dangerous, which are less dangerous. Usually, when you get warnings from radiation, that's a bad thing. That usually means that atmosphere is kind of unstable. But if those appear and disappear, then it's okay. But if you get them persistently, that probably a hint that you are doing something that model cannot actually handle. Some more warnings from dynamics, it's like more, I guess, benign as long as it doesn't crash. It basically just tells you that it's struggling with certain solvers and uses more larger number of time steps. But yeah, it makes sense to look at your .prt file, at least check like if those warnings look like dangerous or not, because sometimes you probably can see from the warning messages that those are really like telling you, please stop and figure out what you are doing, because that's not what the model is supposed to be doing.
Yeah, so
Okay.
Nick, you had a question, Nick Piscopo?
Yeah, I was wondering if one can use these checkpoint files, restart files, for modifying some of the parameters. Like you mentioned several times, mean molecular weight could be problematic to sort of change as part of the evolution of the climate. But can one actually use this save file and try to gradually push?
Yes. Yeah, you can. You can. There's certain restrictions. You can't change the boundary condition files typically in this restart, in what you're going to restart from the checkpoint restart files. But you can change things like insulation, and we do that all the time.
Okay.
Well, you don't change insulation in the restart file.
No. I'm saying that you can use the restart file in your run deck and then change the insulation in your run deck.
Yeah, but you change it in the either in run deck or in I parameter. But restart file itself, like in the Unix world, in a lot of config files which are generated automatically, people put at the top the warning: if you modify this, you will get what you deserve. So with restart files, you should be very careful and really know what you are doing if you change something there, because it's basically
no. He's not. We're not. Yeah, you never change a restart file.
Yeah, I'm not gonna modify the binary files. Just using this as essential initial.
Right.
Yes, that's fine.
That's what he's asking. Yeah, that's fine. That's totally fine, Nick. That's how we do large parameter sweeps. Actually.
Good, excellent.
Yeah. Well, sometimes we do modify restart files, but that's.
But we will not discuss that here.
We are not at this level of tutorial yet.
No, sometimes you need just to remove some field from restart file, because if you change the source code, it may become incompatible with a certain field that you are reading. So that's what we do.
That's even a step further. If let's not modify restart file yet, and certainly not modify the source code at this point.
But I still want to mention that sometimes if you hack the model and the model crashes because it cannot read certain array from the restart file, that's one thing that in certain cases one can do. Just remove that array from restart file, and then the model will be using default values for that array, and that may allow you to continue. But of course you should know what you are doing. I mean, which array you can remove or which you cannot.
It's a pretty rare occurrence.
Yeah.
Well,
okay.
It just happened recently that people had to remove diagnostic accumulation arrays because they were changing diagnostics. So that's like the most common case. What happens? Everything else, like real physics arrays, you probably shouldn't touch anything of that.
Okay, good question, Nick. Any other questions for us?
I have two more if nobody else has some.
Well, let's just see. James, did you have a question? Because your video's on. I thought you might have a question. Go ahead.
Yeah, I do have a question. I'm looking specifically at a pretty early period in Earth's history, 3.8 billion years ago. And I was wondering if I wanted to increase the extent of the oceans, as to what I perhaps would be my options in terms of maybe creating a new topo file or something that would allow me to basically to simulate that.
Yeah, you have to generate all new boundary condition files. You have to create a new topo file, a new topo OC file, a new OIC file, and a new river directions file.
Yeah, this falls even more, but this falls into the new planet. And we will be discussing that tomorrow.
Yes, exactly.
Right.
So Chris Kolos will touch on that.
Yeah.
Because
when you go to 3.8 billion years ago, you modify the solar spectrum, you modify really a lot of things. It's a new planet. So wait until tomorrow after lunch.
But don't hesitate to contact us if you need help creating your new ocean initial condition file and topography. We have the scripts and a program necessary for this.
Great. Thank you.
I just wanted to mention that at least with some input files. If you just omit them completely from the run deck, it is okay, because model will do something reasonable, like you'll use some defaults. But of course, you have to know what you can omit and what you cannot. But if you look at our simpler run deck and notice that certain input file is missing, it's probably not because we have forgotten to include it, but because actually we can use the defaults for that. For example, if you look at the Mars run deck, you will see that a lot of input files have disappeared because we don't care about certain fields and we just use defaults. For example, we don't put river directions there. And what that means that basically if there are no river directions, then the model assumes that there is no water flow between the cells, which is dry, which is okay for dry planet because you don't have actually rivers. So if you form a lake, it forms locally and then evaporates and everything is fine. So there are quite a lot of input files that basically assume some reasonable defaults if you don't include them into run deck. So that may help, like if you create a new planet and don't know what to put there, or just don't want to bother like to create everything, which sometimes is trivial. So
Okay, Aaliyah, I think you had your hand up. Question.
Yes, I did. I know that the other part, did you want to, Dr. O'Connor, did you want to go ahead and ask your second question? I believe I don't want to intrude.
Oh, James, did you have another question? Sorry.
Yeah, I know someone said they had two questions.
Oh, that was Stephen. He's already asked a couple questions. So he said, let other people go first. So go ahead, Aaliyah.
Oh, so I just had a question in regards to the Archean templates that you have for Earth. And does the model have any type of parameters to be able to simulate organic haze formation triggered by methanogenesis? Is that something that could be feasible? Like I've simulated these things in one-dimensional photochemical models, but not necessarily in a GCM. And I was just curious if that's something that is ongoing, or is that something that can be done, or am I out the range?
Costas.
So this, if you want to simulate those things dynamically, this is not possible right now because we do not have an oxide chemistry in the model. We are working on that, but it's not ready. And it will not be ready next month or something. But the way you can do it is you can create from your 1D the model, for example, you can create some layers and make assumptions based on that vertical information you have, and make assumptions on the horizontal. So maybe you can say that the planet is uniformly covered by that type of layer, and then you can use that as an external forcing and calculate that. It's the optical properties will be different from the things we have right now, so it is not simply adding an input file. It will take more work than that, but it can be possible to do it like this. It's but it's non-zero work.
Gotcha. We'll talk more offline.
Sure.
Excellent. Thank you, Aaliyah, for that question. Okay, Stephen, go ahead. You said you had one or two more questions?
Yes. In the crash FAQ, it talks about the DT SRC reducing it. Now, I'm assuming that that means that you get more resolution in a time step. It has a comment about not going below 900. Is that a computational limitation, or is there a problem with the model at that point?
Go ahead, Igor.
Actually, I'm not sure about that limit. It's probably just something reasonable that is suggested, but I think I went to smaller time steps for certain computations. You should just understand that there are several time steps in the model. So DT SRC, that's pretty much the time step at which like single column physics exchanges data with dynamics. So the dynamics has atmospheric dynamics has its own time step, which is called DT in the run deck. That can be very, very short. So that's usually the time step which we are reducing when we get instability, because we assume that it's in dynamics. So that may go like to probably, don't remember what was the smallest one. Like,
I think I've seen 125.
huh?
I think I've seen someone using 125 in this DT thing.
I
Well,
probably
even
used
lower.
even less than that, probably
Even
like
lower.
close to
Yeah,
the
really?
minute. Yeah, close to the 60. So there is also some limit there. I'm not sure. We have to talk to our dynamicists, because they said like it's not like the model will crash. I guess it just becomes inefficient to decrease the model below a certain limit. But yes, 128 is still fine. Smaller than that probably wouldn't help you much, because there are some other mechanisms that can kind of make it unstable. DTSRC, we usually don't decrease it too much, I guess, because basically, yeah, and it also becomes extremely expensive because, basically, the most expensive part, if you are actually running the model as planetary model, is radiation. And radiation, by default, it actually is just run once per 5 DTSRC time steps, just to make it cheaper. So if your model is unstable, then first thing you do, you just call your radiation every DTSRC time step. That's already pretty expensive. So going down with this time step and calling radiation every time step becomes pretty expensive. So I guess at some point, just probably it was already not very practical to go to less than 900 seconds in that case. But I don't think there is anything that prevents one to go down if one wants to.
And I kind of remember seeing a comment in the Rundex that the moment the model starts, you cannot modify DTSRC anymore.
Yeah, that's true. That's one thing, yes, kind of, I guess, is not mentioned enough in the documentation, but you have to restart. If you change DTSRC, you have to restart model. You cannot like start it from your checkpoint for Dynamical file. You have to restart it basically from scratch, or at least from the monthly RSF file. And I guess we didn't discuss it today, but we will probably discuss it tomorrow, how to restart the model from restart file. You just use different iStart flag for that. But yeah, hopefully it will be discussed tomorrow.
No, we have a slide on it tomorrow.
Yeah. So yeah, so you can change atmospheric dynamic time step on the fly. I mean, just change it in your I file, and the model will continue with smaller dynamics time step. But DTSRC, it's a basic thing. The problem is that DTSRC is used basically as a time counter in the model. So if you change it on the fly, that basically means that your timing and probably your calendar will be broken, and the model pretty much will not know which time of year it is, and that's something.
Yeah, you can see. I mean, just for example, I mean, I have these dynamical problems in some of my runs occasionally, and if you change NRAD equal to 1, meaning call radiation every time step, and you decrease DT source, say by, or not, sorry, DT source, DT by, say from 450, I've run mine as low as 112.5. Then I see the per month output takes, say, between 4 and 8 times as long. So your model really does slow down considerably by messing with the dynamical time step. So keep that in mind. If you run into instabilities and you think you're a couple thousand years away from equilibrium, you might have to wait a long time to get there if you have to change these dynamical time steps and the radiation to be called every time step.
Well, that sounds ominous.
Just time, some people have
Yes.
more time than others.
Yes.
And one thing to say, just for historical reasons, for the Earth model, we consider changing NRAD from 5 to 1 a major change that is not, you don't do it lightly, because it affects radiative balance by calling radiation more frequently than the standard one. For planetary applications, you don't really care about that. We don't have that tight constraints, but it is something that you need to keep in mind, that it is a pretty big change in the model, regardless of performance. It's a pretty big change, so you should be doing that sparingly.
You have another question, Stephen?
I do, Mike. When I compiled the rundex for this tutorial, along with some other ones, I got a couple of errors that flashed by that I think were overflow errors, that it was trying to write something greater than 32 bits to a 30-bit point. Is that something that other people are getting, or am I just special in this problem? And I need to look into it more.
Are you talking about the rundeck name? Have you used a very long rundeck name, maybe?
No, I have to retype them, so I try to keep it short.
Because what you say, 32 to 30, is an issue we have in Planet 1.0, which is solved now in the post-processing, because not all of our utilities are able to handle 32, but they can handle 30 characters in the file name. But if it's not that, I never heard of that, what you're saying.
Okay, then I'll try to get some screen caps tonight of what I'm seeing. Okay.
So Stephen, are you talking about warnings that you are getting during the compilation or running?
The compilation.
And my guess is that you are using GCC 10 version.
I believe so. I'll double check.
Yeah, because that was a major change in the compilers, that GCC 10 is much more picky about certain things. I think most of those warnings are just basically just misunderstanding that compiler doesn't quite get what we are doing. But we started to support GCC 10 only recently, so we didn't yet go through all those warnings. So maybe some of those are kind of reasonable, but we didn't notice any unusual behavior in the model behavior. So I don't think that we break anything. It's just sometimes the compilers are too smart. They are trying to figure out certain things that they actually cannot figure out. Like they try to figure out interface to the model, to the function which is called, though we didn't provide the interface. And if it sees that sometimes we use the same call differently, like sometimes we pass integer to function, and sometimes we pass to the same function, like a real 8 or something like that. They think that it's that people shouldn't do such things, so that's why they give you warnings, but they don't understand that it's actually a C function. Like, for example, in OpenMPI call, and C can handle, it handles it just like buffers, and it doesn't care if you pass integer or floating point, as long as it knows the length of the buffer. So it could be something like that. I didn't look through all those messages from Intel 10 because there are just too many, but I think a lot of those were in that sense.
Yeah, I think I should just mention quickly, we have been testing this model with GCC 7 and 8, GCC 7 mostly, but GCC 8 a little bit. But we've done very limited testing with GCC 10. The only reason we put any instructions for GCC 10 was for the obvious reason we couldn't get the model to build on the latest version of Mac ports with GCC 8 because of these problems with the NetCDF libraries. Otherwise, we would never suggest using a compiler that we have not tested very much. But so that just a little bit of a caveat there, that we haven't, Igor's probably right, nothing really terrible to worry about, but I would be a little cautious and using GCT10 for any production runs until we've done a bit more testing with it to make sure that it's working properly, because we really haven't interrogated it fully, in my opinion.
Yeah, but I still want to mention that actually we are now using GCT10 for our regression testing. So basically, like the most sanity checks are done automatically with this compiler, like every night, each time when the model changes. So we know that it is reproducible with respect to number of MPI cores that we are using, that it is reproducible with respect to restarts, so that when you stop model and restart, then it also works fine. So things like that work. So there is nothing obviously broken with GCC10. But we didn't do any production runs. That's true. So we cannot say for sure that sometimes weird things happen.
All right. Well, I'll really try to get those screen caps to you guys tonight. Figure out what's going on.
Okay. Hopefully the ones we're familiar with.
Yeah.
Just I mean, anecdotal thing that in terms like what can be broken by new compilers. For example, I think 10 is still okay, but GCC 11 actually assumes when you have what is integer? Yeah, integer overflow. It just sets the number to max int instead of computing overflow as it was done for previous 40 years. And that actually breaks random numbers generators. That's what we found out. So like, it looks like perfectly legal thing, but things break in such a way. So yes, certain things like that have to be checked when you switch to new compilers. Luckily, that was actually caught by our regression tests, so we could see it. But yeah.
All right. If nobody else has a question, I have one more.
Sure. No one's raising their
One
hands.
question, if I can.
Oh, okay, go ahead, Ricardo. You had another question. Go ahead.
It may not be for today, but I'm curious as to whether this should be asked tomorrow during radiation, or it can be asked today. But the question is, I want to change, I don't think that I really need a new planet, but I want to change the atmosphere. And specifically, that would mean I need to understand how each gas species is put into the model, and therefore how you would want to modify that. So should that be today or tomorrow?
I think tomorrow we're going to, Eric Wolf, who's our radiation person, will talk about this to some degree.
Did I hear right? Did you say ionosphere?
No, he didn't say ionosphere. No.
Atmosphere.
Atmosphere. Okay.
Yeah, I think tomorrow's it's fine. We can go into some details. So I think that Chris Kalos will probably touch on this a bit when he goes through how to build a planet.
All right.
If not, we have another Q&A for an hour. So if for some reason we don't cover it, then ask your question again, Ricardo, and we can go into some detail.
Good.
So go ahead, Stephen.
All right, this is one for Anthony. What information do you need to work up an OIC file?
Basically, just the temperature, salinity of your ocean. Then we have subroutines to compute and to transform to the native format, which is enthalpy and this weird salinity in PSU divided by 1000. But the initial condition would be for the mass, the temperature, and the salinity of your ocean.
And of course, we need a topography of your ocean.
Obviously.
Cool. Well, that's a little bit simpler than I thought it would be. So that's a pleasant change for most of my questions.
Good. Okay, we have another 10 minutes, or we can call it early. Any other questions? Okay.
Did the connection freeze?
Sorry?
Did the connection freeze? Because everyone's kind of frozen on my end. Can everyone hear me?
Yeah, we're fine. We didn't have any freeze here.
Okay. Oh, it's coming back up now. Okay, I'm good. Sorry.
Okay, no worries. Okay, I guess if there's no more questions, then we'll call it a day. So I just want to thank Kostas and Tony and Igor for their help with today's session. And us four will be here again tomorrow, along with Eric Wolf, our radiation person, and a few other folks to talk about different aspects of the model. So tomorrow will be a little bit more people, but we'll only have an hour break for lunch, but we'll still take our 15-minute break. So it'll be not too rough again. And hope you all have a nice evening or day, depending on where you are. Talk to you tomorrow.
See you tomorrow.
Thanks, everyone.
Good night.
Bye, everyone.
Bye.
Thank you.